Hello, I welcome you all to this another interesting screencast. The problem reads determine the angle theta where 50 kg bar is in equilibrium. The spring is unstretched at theta equal to 60 degrees. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We are going to solve this particular problem by using the virtual work method. This is an alternative method to the equilibrium of a particle method, to the equilibrium of a static body method, to the equilibrium of interconnected static bodies method. It is an alternative. So what is this virtual work method? This method states that the total virtual work in a system is equal to 0. Del U is equal to 0. And this total virtual work can be either due to the summation of forces P del U. These are translational forces del U, del R. Okay, you can also have forces, virtual work due to couple moments, which is M del theta. And when we sum up the virtual work in a system, it gives us 0. Given a force P, okay, or F, and then given the virtual translational displacement dr, if both of them are supposed to be collinear or parallel, and if they are in the same direction, then you have positive virtual work. Otherwise, you have negative. The same goes with the couple moment and the rotational virtual displacement. They are supposed to be collinear or parallel, and if both of them are in the same direction, then the virtual work developed is positive, otherwise it is negative. So basically this is the method that we intend to use. So let's straight away go to solve this particular problem. All right, so first things first, we draw the free body diagram, and then after the free body diagram we are going to draw another diagram, free body diagram of a deflected or displaced configuration of the same system after applying a virtual displacement. And then we'll have virtual displacement equations that we're going to use later on in the virtual work equation. All right, so at A, and in this system, this is a single degree degree of freedom problem. And by this we mean we can locate any point within the system itself or the force just by using the one coordinate system, which is theta. All right, and in this particular problem we are assuming that there is no friction. Okay, so at A we are only going to experience normal force. At B we also just experience normal force, and then we have this spring. Let's do a section like so. So once we do a section there, we are going to have some spring force like so. We'll have some spring force there like that, and there like that. Okay. And then we also have the weight of this particular bar, which we are going to label W, and is acting at the centroid of this particular bar, which is just the mid span. Okay, at 2.5. Okay, so it's acting at 2.5. Let me just indicate that at 2.5. All right, there we go. Great. Okay. So we have so far everything. Let's apply. Let's label these particular forces. So this we are going to call it Bx. Then this one Ay. Then this one we'll call it Fs. Okay. So we know that Fs is equal to, according to Hooke's law, the spring constant times the stretch, and K itself is given already, is equal to 600 newtons per meter, and S is equal to L final minus L naught, and we've been told that the spring is unstretched at theta equal to 60. So therefore unstretched length is just going to be equal to the length of the bar, which is 5 cos theta at theta equal to 60 degrees. Therefore L naught is just going to be equal to 5 cos 60 degrees. Okay, and then L final, we don't know what it is, so just write it as 5 cos theta. Okay, therefore Fs, we can simply write Fs as equal to K, which is 600. Okay, L final, which is 5 cos theta minus 5 cos 60. Okay, this therefore gives us, if we are to simplify this, we have 600 by 5, so this becomes a 3000 cos theta minus 600 times 5 cos 60 minus 1500. Okay, all right, so there we go. That is Fs. Okay, so now let's apply a vector displacement. We are going to choose our reference. Let's choose our reference. Our reference, our fixed reference, our fixed reference is, we're going to pick this point. Let me call this point as point AB. Let me call this C, then this one D is D. Okay, all right, so I'm going to apply a vector displacement. You can apply it at either point B, point A. It's really up to you, and it's up to you to choose which direction. Okay, so I'm going to apply it myself in this direction like so. I'll apply it in that direction like so. Okay, that is my vector displacement at this point like so. Okay, so I'll call this as, I'll call this as my del x a. Okay, so let me draw the deflected or displaced configuration. So I expect a system like so. Once I do it, expect something like this. Okay, we can something like so. Okay, so what has happened here? At this particular point, at this point here, we expect this point to have moved, this point to have moved down, and to have also moved this direction. Okay, all right. So this is equal to, this one is equal to del y c, and this one is equal to del x c. But of course here we're just interested in the one where we have a force. Okay, we are also going to have a movement here, a movement down here, like so. We have this one. We can call this one as your del y b. Okay, but we are not interested in that one. So we have written everything that we need, but the points where we are going to have virtual work is at point C in the vertical direction and point A in the horizontal direction. Okay, so let's write down now our reference system from I mean the equations that locate these particular points. So from this point, go down like so. We locate point A there like so. Okay, so that's one of it. And then the vertical direction, we'll move. We're going to locate it from there like so. Okay, like so. Like so. Great. So these are the 2 points that we are interested in. The vertical and the horizontal at T, at A. Right, this is about it, yes, for the locations. Okay, there we go. Just clean it a little bit. Alright, like so. Great. Let's label it. So this one, we are calling this as the XA. Alright, D is our reference. And then this one we are calling it as YC. Okay, so let's write down these equations. So XA is just going to be equal to, from D to that point there, we are saying this just becomes 5 cos XA is just equal to 5 cos theta. And the vector displacement will be del XA. We are just finding the first derivative of this particular expression with respect to theta, and this becomes minus 5 sine theta del theta. Okay, and this one I'm going to write it in, I want absolute value. Okay, because the actual sign will be given in the final equation of a virtual work, where if our forces are in the same direct, force and the displacement in the same direction is positive, in the opposite direction is negative. So this therefore just gives me 5 sine theta del theta. Then we have the other one, which is YC. YC is equal to, we are locating point C in the vertical direction. So point C is half the length. So this is just 2.5. 2.5 sine theta. Therefore, finding the first derivative, here we are trying to now express the virtual displacement in the vertical direction. Del yc is just going to be equal to 2.5 cos theta del theta. Okay, right. I think we've written the expressions. We need to move on. We say 2.5 cos theta del theta. All right. So now let's apply the virtual work equation. So we know that del u is equal to 0, the total virtual work. Okay. So let's start with point A. Point A, the spring force and the virtual displacement are in the opposite direction. Therefore, we assign what? A negative, right? So negative Fs, okay, del XA. Okay, del XA, all right. And then at point, of course, maybe somebody may be asking, what about AY? AY, we don't have any displacement in the vertical direction at A. Therefore, AY will not cause any virtual work. So let's move to C. To C, we have W, and we also have the virtual displacement del YC, and they are in the same direction. Therefore, this we are going to have a positive value. So W del YC. Of course, the virtual displacement in the horizontal direction, del XC, we don't have any force in that direction, therefore no virtual work in the horizontal direction. And at B, BX, in the horizontal direction at B, no virtual displacement, and in the vertical direction, we only have the virtual displacement but no force, therefore no work in both cases. Therefore, this is just going to be equal to 0, and so is point D. We have a force there, but we don't have any virtual displacement, okay, of our system. All right. All right, so there we go. So we have this equation. We just need to plug in everything that we have. Let me just calculate W. W in our case is just going to be equal to 50 kg by 9.81. And once we do the calculation, we have 50 by 9.81. This gives us a 490.5 newtons. So let's replace in the values there. Fs, we calculated Fs already. So Fs is just going to be equal to minus 3000 cos theta minus 1500. Okay, del XA. What is del XA? It is a 5 sine theta del theta, then plus W, we said is a 490. We calculated that already, 490.5. Okay, and del Y is just a 2.5 cos theta del theta equal to 0. Okay, so we can factor out del theta like so, and then we have minus 3000 cos theta, then plus 1500. Okay, then 5. Let me multiply this in advance. Okay, so we have minus 3000 by 5. So this just becomes a minus 15,000 cos theta sine theta. Then we have plus that's 1500 by 5. So this is 7500 sine theta. All right. Okay, and then we have a plus 490.5. We multiply that, sorry, let's multiply that also. 490.5 by 2.5, 2.5 by 490.5. So this we get a 1226.25 cos theta. All right, equal to 0. So 490.5 by 2.5, 1226.25. So we know that del theta is not equal to 0, right? But this part is the one that will be equal to 0. We need to make that equal to 0. So what can we get rid of in this equation? We can divide through by cos, right? So cos there cancels out, and that side it cancels out. Okay, so here we have cos, this part goes, and there we have tan. Okay, so we're going to have an expression like so. So we'll have minus 15,000 sine theta, okay, plus 7,500 tan theta, plus 1226.25 equal to 0. Okay, so we need to solve this particular problem. We need to solve this particular problem. How best can we solve this? So we have sine, we have we need to solve this. All right, so one of the methods is, right, so how best can we solve this? We can solve this by using one of the methods would be to use the trial and error method, which I just want to use right now. So let me take this equation here like so. So now what I'm going to do is I'm going to say this will be my function. My function will be expressed as a function of theta. So this trial and error method, normally how we do it is, imagine the solution is just at this particular point. We have negatives this side, positives. So we intend to find two values, one negative, the other one positive, and then we keep on iterating, and as we iterate, we're going to slowly becoming closer to the solution or converging to a solution. Okay, so let me draw a table here quickly so that we start working. There we go. This is a trial and error. Okay, and our interval for theta, we are saying theta will be in the interval, or the domain for theta is from 0 to 90 degrees. Okay, so there we go. We have theta there, and then we have this function of theta. So start trying out these values into this particular expression. So let's start with 0. Once we plug in 0, what do we get? 0 0, we have just a 226.25, right? And then let's go to 20 degrees minus 15,000 sine 20 plus 7,500 tan 20 plus 1226.25. So this gives us a minus 1174. Okay, quite a huge value, 28. So we know to say somewhere in between 0 and 20 we have the solution. So begin to iterate. This is one of the points where we have the solution. We begin to iterate between 0 and 20. Okay, so get the average of the two, which is a 10. So plug it back in the system. So say minus 15,000 sine 10 plus 7,500 tan 10 plus 1226.25. So this gives me a minus 56.02. So of course initially we had to get the average of this. So now we get the average of the smallest values. So far positive and negative, so we get the average of 0 and 10, which is a 5. So we keep on doing this process. Yes, it can be a bit boring, understand. This is one of the methods. Minus 15,000 sine 5 plus 7,500 tan 5 plus 1226.25. So we have a 575. So we get the average of the two. 10 and 5, we have the average of 7.5. We plug it in. So we can keep on doing this. Sine 7.5 plus 7,500 tan 7.5 plus 1226.25. So we have a 25575. Okay, so positive and positive, smallest positive, smallest positive, and smallest negative. These two. Average of that is 10 plus 7.5, 17.5 divided by 2. We have 8.75. We plug it in. That's minus 1500 sine 8.75 plus 7,500 tan 8.75 plus 1226.25. Okay, so we have 98.76. Okay, so we keep on doing the iteration. So again, the smallest values will be these two in the negative and positive. So 10, that's 18.75 divided by 2. So we have a 9.38 degrees. So what does this give us? That's minus 15,000 sine 9.38 plus 7,500 tan 9.38 plus 1226.25. Okay, so we have a 20.45. Okay, so we keep on doing the iteration. Let me draw another table. I draw another table here. Okay, so we keep on doing this boring process. Sorry. Okay, again we are getting the smallest values, the smallest on the positive and the smallest on the negative. So again it's 19.38. That's 10 plus 9.38 divided by 2, 9.69. So we'll have a 9.69 degrees. We plug it in. Sine 9.69 plus 7.5, 7,500 tan 9.69 plus 1226.25. So this gives us a minus 17.86. Okay, so now it begins to reduce. We get the average of 9.38 and 9.69. 9.38 plus 9.69 divided by 2, so we have a 9.54 degrees. We plug it in. That's minus 15,000 sine 9.54 plus 7,500 tan 9.54 plus 1226.25. So this gives us a 0.66. So we can get the average of the two. We are getting closer to the solution. It is just somewhere between these two values. Okay. So 9.69 plus 9.54, and what we are seeing this side, these are the errors. Want the error to reduce point. So this average of the two gives us a 9.62. Let's plug in that one. Minus 15,000 sine 9.62 plus 7,500 tan 9.62 plus 1226.25. Okay, so we have a minus 9.22, so meaning we need to get the average of the two. 9.54 plus 9.62 divided by 2, that's 9.58 degrees. What do we get? So we have minus 15,000 sine 9.58 plus 7,500 tan 9.58 plus 426.25. So we have a minus 4.28. So we get the average of the two. 9.54 plus 9.58 divided by 2, that's 9.56. Okay, let's try that one. Minus 15,000 sine 9.56 plus 7,500 tan 9.56 plus 1226.25. So we have a minus 1.81. Average of the two again. Okay, smallest negative and smallest positive. 9.54 plus 9.56, of course, is 9.55. Let's check out this one. That's minus 15,000 sine 9.55 plus 7,500 tan 9.55 plus 1226.25. So this gives us a minus 0.57. Alright, so the solution is somewhere between 9.54 and 9.55. Alright, so even when we get the average of the two values, this value and this value, okay, it will just have a number of decimals, right? So we can pick the one with the smallest error between the two because we know the solution. So this one has the smallest error, seeing this one compared to this. Okay, so this has the smallest error. So therefore theta, one of the solutions for theta is approximately equal to 9.55 degrees. Alright, I think this is about it. You can check it out and plug it in here and see how it works. This is the final approximate that we have found. Okay, using the trial and error method. All right. I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.